Thanks a lot for inviting me here. My talk is going to be about compactifications in string theory, by which I mean solutions where there is an external space-time factor with maximal symmetry and some internal compact space. In particular, I'll focus on the presence in these solutions of sources such as D-branes or O-planes. These are important in ADS-CFT because they realize flavor symmetries, but also we know that O-planes appear to be necessary for the existence, to realize these solutions. However, it has been hard to find examples where these sources were properly taken into account. The Beck reaction actually was taken into account in the internal space. And for this reason, people have often resorted to smearing them, namely replacing them with a distribution which is spread out all over the internal space. This is fine for D-branes, but O-planes are supposed to sit at the fixed points of involutions, the two symmetries. So that's not OK for O-planes. And at this point, let me thank actually Liam McAllister for warming up the crowd about this issue this morning. My plan is to first review some general progress in finding solutions in string theory, compactifications in string theory. And then I'll focus on, I'll show you how to introduce these Beck-Reacted sources. By now, we know how to do it in many classes of examples. And I illustrated with some examples, actually, with some very simple examples. And then we'll see whether we can use any of this progress to find some new de Sitter models. So, OK, let me start with the first part. So a general comment, it has proven, experience shows that it's better to use, to start a systematic classification of BPS solutions rather than using some ad hoc ansatz. So at the beginning, this appears boring, but in the end, it pays off. The methods for doing so have been introduced long ago, such as G-structures or generalized complex geometry, or in particular the pure spinor equations that we found many years ago. But I would think it's fair to say that it's the proper conceptual home for these concepts hasn't been found yet. Why exactly these methods work so well? Why do they simplify the task of finding, especially supersymmetric compactifications? One possibility is the theory calibrations, which are forms that are originally introduced in order to tell you where a source, a probe, a D-brane probe, for example, should sit in order for it to be BPS. And later it was found that the supersymmetric equations in supergravity imply some nice equations on these forms. So for example, here there's the collective D-brane calibration, namely for several degrees, so forms of various dimensionalities, which is this polyform phi. And this equation, this is the equation that this has to solve for supersymmetry, and it has been found long ago. For some reason, the one for NS5 was only found last year. Here, just a couple of comments. H is the Nair-Schwartz flux. F is the collective polyform for the Ramon-Ramon flux. K is the Killing vector associated to supersymmetry. And this is a natural pairing among forms. So empirically, the first of these equations, the D-brane calibration equation, is already enough to start a classification effort because it proves to be equivalent to supersymmetry for many problems, such as compactifications in high enough dimensions. And in particular, you can use it, for example, to recover the old pure spinor equations found many years ago. But also, we found much more recently, last year, basically, that you can use them to find a matrix-valued version of these pure spinor equations, which is particularly effective at finding solutions with extended supersymmetry, n equal 2, n equal 3, and so on. So if you look more generally, if you want to generalize the external spacetime, or you don't even want to have a factorization, then the story is different. The first equation, the D-brane calibration equation, is not enough at all. You need to supplement it with the NS5 brane equation that I showed you earlier, and also with a bunch of others. So in some situations, you can find an elegant system which is completing the calibration spirit, which is equivalent to supersymmetry, but it's still not possible in general. And I think from time to time, I revisit this issue. I think it's still not completely closed. So all this was for supersymmetric compactifications. A couple of comments about how to break supersymmetry. So we have some work in progress where we found, after trying for many years, we found that we are far from having a general theory of how to do this, but at least for Minkowski solutions, we know that in some classes of examples, we can modify the pure spinor equations for supersymmetry, basically the ones we saw in the previous slide, by adding a single term which breaks supersymmetry. Namely, the BPS equations are no longer satisfied, but the equations of motion still are. Again, we don't have a general theory, but this appears to be possible in various examples. And then, so examples that I'll use implicitly today are, methods that I'll use implicitly today are method of consistent truncation. This used to be very tough, but as was, for example, reviewed by Henning Zamtreben, it has become much easier recently. And then well, sometimes you find also that, as we'll also see, that after you have learned enough from the supersymmetric case, you can apply what you have learned to set up a direct solution of the equations of motion. So let me now showcase a few solution classes. The one, so there's first, let me comment on this one. This is the class that I've been working on for a few years now. We have kept improving it and improving it. I think now the dust has settled. We will see it better later. It's a best class in that here we have a complete classification. We know all the solutions, they fit in one line, as we will see. And here the internal space is an S2 fibered over an interval. There is also a class where instead you have, in IDS5, you have a class where the internal space is topological three-sphere fibered over Riemann surface. And sometimes you can even change various defect points. You can change this topology to introduce something more interesting. There's also, in IDS4, there are two classes that I like. One is topological three-sphere fibered over maximally symmetric three-dimensional space, and another consists of a topological two-sphere fibered over a Kähler-Einstein for manifold or a product of Riemann surfaces. And okay, so in, actually, let me complete it, this table with IDS3, where actually these are very special solutions, but I like them a lot because they realize some strange, exotic, exceptional superalgebras. So I don't have time to comment on all of these, but for now, let me, so for example, focus on this one, where the metric looks like this. So maybe doesn't look like much at first, but it's really nice because you can play quite a bit. This is a degree 6 polynomial. And this is the topological two-sphere I was talking about. This class of metrics is dual to Chern-Simons matter theories, and it generalizes, for example, the Guarino-Jafres-Varela solution, if you know it. So some other comments. So, okay, well, this is just to show you an example for now. All these, I should say, all these examples, well, this is complete. These are just some examples, some particularly nice classes that are nice examples of a more general classification effort, which will require me more time to explain. But often what you end up with after all the geometry, after you have used all these geometrical methods, is just some set of PDEs that looks nasty. But the accumulation of these efforts is helping, because sometimes you can recognize that something similar appeared in a different dimension, and that helps you to find the correct coordinates to simplify the PDEs. And another comment, we'll see soon that in all these classes, I can introduce some explicit back-created sources. So and that actually takes me to the second part, so including sources. So first of all, many solutions that we know have no sources at all, and that is easily explained. The internal space, what ends up being the internal space, starts its life as the set of angular coordinates that surrounds the source, so it doesn't intercept the source. So after you take the Neo-Horizon limit, of course, you won't find any source at all. And this is the case for this example. And so the sources kind of dissolve in the Neo-Horizon limit. This is a familiar phenomenon, but if you do this when there is some other source, which you're not zooming on, then your set of angular coordinates might actually intersect this other source, and in that case you will still have it. It doesn't dissolve. The second type of source doesn't dissolve upon taking the Neo-Horizon limit. Okay, this is more or less the reason that you can expect any source, any back-created source, to exist at all. But why Is this really helpful? Well, first of all, it is unclear whether all ADS solutions come from a new horizon limit of anything. And even when we think we have a good reason to believe so, concrete explicit solutions that represent intersetting brane systems are hard to come by. For example, for this complicated system here, good luck finding the explicit Beck-Riater solution. So a better strategy proves to start from some analytic classes and explore what the boundary conditions give you. Now, first I need to remind you, most of you probably know this by heart, but I need to remind you the Beck reaction, first of all, that D-branes or O-planes induce in flat space, to be for starters. This is the metric in all these cases, both for DP and OP planes. And H is the harmonic function of the transverse coordinates. Let me show you some plots, actually. For D-branes, you see. So in red, I show the region where the supergravity approximation breaks down, either due to strong dilaton or strong curvature. So you can see that this happens for D-branes. And for O-planes, it's even worse because you see that there is a region where the H function becomes negative, which of course makes the metric lose completely its meaning. An exception is the O8, for which this doesn't happen. However, if you take the limit where A goes to 0, you have that the dilaton actually diverges on top of the object. And this will be a case that will present itself several times. So let's see how we can use this. For example, let's use this ADS7 class that I promised. This is the most general ADS7 solution. The metric, as I promised, now fits in one line. And the internal space is, like I said, is S2 fiber over an interval. So in this cartoon, this is the direction Z, and this is the vertical direction is supposed to be this S2. And the BPS equation just says this. So it's very easy to find solutions. Moreover, all these solutions have a non-supersymmetric evil twin, which is basically obtained by changing some numbers in an apparently mysterious way, so that the equations for motion are still satisfied, even though the BPS equations aren't. In work in progress, we are finding that most of these are actually unstable, but this will be of no concern for the rest of this talk. It would be of concern for the previous talk, but this is work in progress again. So far, this was perhaps a bit formal. You maybe want to know whether this can be made into compact internal space, and I haven't told you how to do that. Well, let's see how to do that. What you need to make sure is that the S2, this direction here is the S2, can cap off smoothly at for some value of Z. And what should happen? Well, so this is the volume of the S2, so you should make it go to 0. And you can achieve that by simply making alpha go to 0. On the other hand, here, if you don't want to introduce a singularity, you should have this to be imposed that this goes to a constant, so alpha double dot should also go to 0. And that's it. So that's just a boundary condition for smoothness in these solutions. Another observation is you can let F0 jump. By definition, that's a D8 brane. And this is in no contradiction with this metric, because you can just make sure you can change your alpha, okay, so the triple derivative, but you can just make sure that the thing is still continuous, so that all the coefficients are still continuous. It won't be differentiable. The lack of differentiability represents the Beck reaction of the D8 branes in these solutions. Okay, so with these two ingredients, we can already find infinitely many solutions. But let's see whether we can find something even more exciting from the point of view of today's talk. So what happens with other boundary conditions? And so, for example, I can, instead of sending both alpha and alpha double dot to 0, I can send alpha only. And then, as I anticipated, this will become singular. So you see the solution is now singular. However, by comparing it with the Beck reaction of D-branes in flat space, we see that it's exactly the same expression with the function h that does this, that diverges exactly like D6 would be. So then you want, instead of throwing this solution away, this boundary condition in the garbage, you might say that it represents a D6. Similarly, if you impose now only that alpha double dot equal to 0, not alpha, then you find the same behavior as it would at the boundary of the hole that I observed for the O6 in flat, or OPs in general in flat space. And for all these solutions, you can actually even analytically continue inside the hole and find this negative pole behavior that we formally have in the flat space solution. If you play some more, many boundary conditions don't make any sense. I mean, they're not physical, they're not realized, but another one that does is this, which corresponds to an O8 of the infinite divergent dilaton variety. So the dilaton diverges right on top of the object. So to be sure, so first of all, it's not always so easy. This is a particularly nice case. Sometimes, especially when there is so the solution depends non-trivially on more coordinates. Working out the boundary conditions is a lot more complicated. And also, well, I'm not crazy. I mean, of course, these are supergravity artifacts. They shouldn't be taken seriously. We know that they're not physical, and we expect them to be resolved in full string theory. And in some cases, we can demonstrate that to be the case. For 6 planes in flat space, we know how to do it. For 7s. But my point is that when we encounter this phenomena for compactifications, we can just say, oh, okay, I recognize that it's the same artifact, supergravity artifact that I had for the solution flat space. So perhaps I shouldn't throw away this solution. If you're not satisfied, since these are ADS7 solutions, I can go a little further. I can use holography. These are ADS solutions, after all. For the ADS7, I actually know the duals. There is an effective field theory description in terms of just a chain of gauge groups, a quiver. And using some anomaly matching techniques developed recently, you can just compute the A anomaly, for example, and which you can show that it matches with the answer that you will get by holographic methods, very well established holographic methods. It's just an integral for using that metric that I showed you. And so this is just an example. It shows you can show that it works in infinitely many cases. Most impressively, it works even when there are these strange sources such as the O8 with divergent dilaton. The check still works out. As an aside, there is an alternative to O-planes, which is sometimes touted as being interesting, which is called the nest-fold, where you take a non-compact solution and you make it compact by gluing it back to itself with some S-duality transformation, element of SL to Z. It's a similar idea to F-theory. I was a bit skeptical, but in some solutions you can actually compute pretty explicitly, well, the free energy as an integral, as in these cases. But it's also easy using methods developed by Gerhardt and Witten to propose the field theory dual. And using localization computation, which turns out to be easy, you can, again, check that the free energy this time works out pretty nicely. So, okay, this is perhaps an alternative to using O-planes, which might be interesting in the future. Anyway, coming back to sources, let's forget that aside now. Here's the table I had before with some examples that I consider to be nice. And now you see that for ADS7 we saw it together, but so for all the other cases there are sources that you can introduce. And in particular, sometimes you have solutions which are very complicated where even 3 of these sources appear together in the same solution. To be sure, there are other classes of solutions which are also nice, which have been found by others. I'm not the only person on the planet working on these problems. I would say, however, so in these cases you don't have orientifals per se. Anyway, so but this, I think in particular in this case this can be improved. So anyway, let's see if we can use this progress as an inspiration to find some de Sitter solutions, and this will be the last part of my talk. Of course, it will be more speculative, but let's try. Since we have learned how to introduce sources and back-related sources, let's use it for something. And so the first model we'll see has an internal space which is now a compact hyperbolic 5-space fibered over an interval. The interval was actually originally an S1, a circle, which has been orientifolded. And now after the orientifold, you have 2 O-planes. One is the O8 we have seen so far, which I now call O8 minus, and the other is that I call O8 plus, is a variant which has the same effect in supergravity as a bunch of D8 branes. So around this point, the dilaton is actually finite and everything is nice, so you can just trust your equations of motion, and you work out some boundary conditions. Using those, you can solve the equations of motion perturbatively, and you can use this perturbative solution as a seed for a numerical expansion. Now, for a numerical evolution, playing a bit with this numerical evolution, we were able to find some solutions that look like this. Now, so at first you say, okay, just like in the ADS case, at first you see, here there's a singularity, maybe let me throw this away. However, after you have seen this O8 singularity a million times, finally you recognize it. You say, no, I shouldn't throw it out. It's the same behavior as an O8 minus in flat space. And so then you can check better, even the coefficients work. So, well, okay, perhaps we shouldn't throw it out. Now, inevitably, as I showed you in the previous part of the talk, there is a region here where the dilaton curvature explodes and supergravity breaks down. You can make this region smaller and smaller by using this particular property of the equations of motion. But okay, you can never eliminate it. So if you want, we can't claim complete victory, because here we don't really know what's going on. Presumably, the string theory corrections, the full string theory equations of motion will come into play here and will fix this value C, this rescaling C to some particular value. Or, well, perhaps the solution won't even exist. But I think this is a good first step. Once again, why we think that this is interesting, because the hope that this solution is sensible comes from the fact that at leading order, the behavior is exactly the same. Leading order in the distance from the object, the behavior is exactly the same as the one in flat space, which we know. So also in supergravity in flat space, we don't know that we wouldn't know that this solution makes sense, but we believe it does, because we know that in string theory an O8 minus exists. In case you don't like this O8 minus where the dilaton diverges, perhaps you find it exotic. Well, we've tried with some other objects. The internal metric now changes a bit, and it's inspired, in fact, from one of the ADS7 solutions that I showed you, which breaks supersymmetry, the evil twins. You start from that, and you can easily modify it so that the internal space, now you have, instead of ADS7, ADS4 times a compact hyperbolic space. We started from this analytic solution, and we started bringing numerically lambda up, slowly, until we finally managed to make it positive without losing the same behavior that we had here. Remember, I recognized the solution with the No6 in the ADS7 case by the fact that I hit the boundary of the hole. And this we can still do for these models. Now, is that enough to claim victory? Well, so if you're curious, you can keep going until you can say, I remember that you said that for the ADS7 solutions with those sixes, you could even analytically continue inside the hole. Can you do that in this case as well? Well, so I don't know whether you should take this too seriously, but let's say we're getting closer. The numerics is not entirely the same, but there is some amount of numerical error that we are trying to tame. On the other hand, perhaps this is not really a physical request. So I feel that to make sure that these solutions are physical, it's better to use some other more physical arguments, such as probe analysis, putting some probes on top of these. Okay, so my time is almost up, so here are my conclusions. A lot of progress has been achieved in the near future in finding ideal solutions, especially with localized sources and no planes also. And we have tested such solutions using holography, and they seem to be sensible. And sometimes we can even break supersymmetry. So using all this progress, I think it is time to at least try to find the Sitter solutions. Using numerical analysis, we started finding some solutions. There are, of course, in these solutions, regions where the supergravity approximation breaks down. And so you might be disappointed by this, and you might say, okay, go home, you haven't achieved anything. But this is inevitable. we always said that we wanted some solutions with O planes in order to find the zeta solution. Well, okay. If you do want solutions with O planes, you better learn how to deal with them. Thank you.
Questions for Alessandro?
So for the Sitter solution and the ADS-8 solution, is it correct that you can make the internal space as small as you want? Because if it's true, then you would expect an 8-dimensional effective field theory. But if you check the terms in that theory and they're scaling with dilaton and volume, there is no ADS, neither a de Sitter solution.
No, we never claimed that we can achieve scale separation. So one thing at a time. So there are many things that could be wrong about the solution. So there could be no scale separation beyond the fact that we don't know what happens in the Storm-Gappy region. There could be no scale separation. Also, there could be no. It could be unstable, for example. What was the question again?
But is there an effective potential? Maybe that's my question.
Right. Well, the effective potential. So I can't compute the effective potential because I don't know the full string theory equations of motion in that region. Is that a fair answer? So, I see that you might be disappointed by the fact that we can't say anything about this region where we don't know the string theory equations for motion. Ideally, if we switch to a different duality frame, we don't have it. I think the thing to do here is to test the subleading behavior of this solution. Of course, so I'm aware of the fact that some people complained about the subleading behavior for this solution. And so ideally, you would simply test it not ideally. I think one way to go is to test this subleading behavior by using some physical tests, such as introducing probes. I don't know if that satisfies you.
Hi. If I understood correctly, your de Sitter solution had a modulus, right?
Well, so this dovetails with Thomas's question. So this the modulus you're talking about is presumably this C, right?
Yeah. So.
And when you mean my de Sitter solution, you mean the 0828?
Yes.
This one.
Yes.
So here, this one is a modulus only insofar as it don't take into account the full string theory equations in this region. This is a symmetry only of the supergravity equations for motion. When you put the string theory corrections, there is no, it is not a symmetry.
That's right, but the thing that worried me is that if I understood correctly, you also found that the action depended on this parameter. Right?
Good. So, right. So the problem is that, so you find that it depends on the, so in order to, good. So really the real computation we cannot do, as I stressed already many times, because we don't know the full string theory solution. However, so you might try to play the formal game of evaluating the action for this, with supergravity, ignoring everything else. And the problem that we encountered is that so we tried, although we don't know the full solution, we tried anyway. The problem is that we found many ambiguities in how to evaluate this, which depend on basically on the boundary conditions that you're imposing at this 8 minus. So there's a boundary condition that we impose that works well, but you can wonder whether there are subleading boundary conditions that you should still impose. Depending on those, this C can be interpreted as a field or not. I don't know if that was clear. So in other words, if you are just working in supergravity, I'm afraid that it's a wild goose chase to understand what the boundary conditions for your fields are going to be in this region here. Because just in supergravity is not a complete, we are rediscovering the fact that supergravity is not a complete theory of gravity. And we have to take some decisions when we go to a high energy region. I don't know if that satisfied you, probably not. So C, in other words, this rescaling C has something to do with the fluctuations of the field, because you see that it changes the metric and phi. However, so suppose you are doing a Kaluza-Klein expansion then what modes do you keep and what modes you don't depends on your boundary conditions, and for that this might not be allowed at all as a
Presumably the boundary condition should be such that when you evaluate the on-shell action, they should not depend on any parameter, because otherwise you are not minimizing the action.
I agree, yes. The thing is, I don't know whether this is even well-defined question in pure supergravity alone.
Okay.
Yeah, maybe this is a beyond scope of your talk, but you didn't mention your AD8 solution, ADS8 solution.
No, it's not beyond the scope, it was beyond the minutes. So it is, so Hiroshi is asking about a very similar solution. We published these two papers almost in parallel. There's also, with the same methods, we were able to find an ADS8 solution, which is kind of similar to this, the sitter model here. It has ADS8 times an internal space, which where there's at that time only an O8 minus the equator. The presentation would have been parallel for that very similar for that solution. And the same questions that apply to this model would apply there. Namely, there is again a strongly coupled region where we cannot claim to have solved the full equations of motion because we don't know them. But at least the leading behavior works even with the right coefficients, and there is a question about the sub-leading ones. At least for the ADS8, one could hope that maybe someone can prove us wrong by some bootstrap computation, for example. I don't know, so maybe someone in this audience.
Okay, so let's thank Alessandro.